So we're fortunate to have Jim Davis from UCLA. Jim is going to talk about smart manufacturing, the practice of real-time data and manufacturing intelligence. In fact, he's the prime mover behind this Sesame, the co-PI for Clean Energy Smart Manufacturing Innovation Institute. He's the IT and Vice Provost for Information Technology and Chief Academic Technical Officer, Technology Officer at UCLA. He also happens to be a professor of chemical and biomolecular engineering at UCLA. So he has broad responsibilities focused on the investment and deployment of IT in the university's academic research, education, and public service mission. He has accountability for university-wide planning and strategic investment in computational research, research informatics, education technologies, mobility applications, research and education, data strategies, privacy and security, and internal and external community partnerships. In other words, he makes sure that nobody gets into the UCLA. So he also oversees UCLA's Institute for Digital Research and Education. As I mentioned, he's also a professor in chemical and biomolecular engineering, and where he has done research and consulted extensively on artificial intelligence, machine learning, intelligent systems, monitoring and control, and data and modeling systems across diverse industries, including chemicals, refining paper, packaging, metals, and glass. And that is the reason why George wanted to come here and talk about it, in addition to the fact that he's the one that is primary behind this Sesame initiative. So he has worked with industry, which is good. That means he knows what the real problems are. He worked with Amoco Chemicals, and also heard that he's from Chicago, my side. So,
thank you very much.
Yep.
So I guess first of all, I really appreciate being here. I guess I should put a little color or background to that introduction. I appreciate you going through it. What it really means is I chase around UCLA trying to understand what each of the researchers are doing and realize that I don't know a lot going forward. So we just chase around. The other thing I wanted to mention, too, is for those of you who may know Mike Cutlip on the campus here, he and I go back many, many years. We actually used to scuba dive all the time, together, if you know him. But he's been telling me about University of Connecticut for years and years, so I'm actually very, very glad to be here finally, because he's been talking about what a beautiful campus it is, and he's absolutely right. I really appreciate being here. So what I'd like to do is, well, let's see, one other thing I should mention, too, is Clean Energy Smart Manufacturing Innovation Institute. It was actually pronounced correctly, SESME. One should understand where that acronym came from. When we were writing the proposal, we couldn't think of a name of the institute that was clever, and so we just said, we're going to call it Clean Energy Smart Manufacturing Innovation Institute as a placeholder, and we'll come back to that. But someone pronounced it, said, hey, that looks like SESME, and so it stuck, and so we never changed it. So that's how the thing got its name. But anyway, what I'd like to do is, one of the things about smart manufacturing, and I'll define it in just a minute, it's really about what can you learn by stepping back from systems. I know from a research standpoint, we all want to go into depth, and we want to look at things in great detail. But one of the things we've asked ourselves from a smart manufacturing standpoint, what can you learn when you step back from things and look across systems and look at enterprises and these sorts of things? So this will be a talk that's not going to go into depth. I don't think I even have a single equation in here. But think about it as, what would you see if you really step back from an entire company, look at entire supply chains and so forth, and then how can you approach it with that kind of perspective. So what I'll do is take you through kind of a broad, this is going to be a breadth cut of things with respect to smart manufacturing. And if you'd like to go into depth on any particular area, happy to do so in the question and answer or later on. Also, I guess this is being broadcast, is that right? I was going to say with a smaller group, please feel free to make this much more of a dialogue. It doesn't have to be a talk, so please feel free to interrupt as I go forward. Well, that's not... Okay. Let's do it this way. I'll just do it this way. So what is smart manufacturing? From our perspective, the term was first coined about 2006, and at that time no one was using it. We had a particular definition. If you fast forward today or if you Google it, you come up with millions of hits. It's being used to mean almost everything. And so as time has moved along, the meaning of smart manufacturing has become less and less clear. So I'll try and give you what our definitions is going forward. But the top one here is probably the most important one. The operational and business and technology practice of radically increasing the application of real-time data throughout the manufacturing enterprise. And the keywords here are changing the operational structure. I was mentioning this a little bit this morning, but basically if you look at a manufacturing enterprise, everything has been built up over 100 years around the facilities, the actual operating equipment. And when you look at the information technology over the past 40 years, it's been built up around the operating equipment. As a result, lots of things now have been built up in a highly vertical, highly compartmentalized manner. But a lot of the opportunity, whether it's energy, it's production, precision, what have you, is around being able to look at the enterprise. Now, that's been around, from my perspective, for years and years as well. But we now have some technologies that allows us to go after it, again, in some new ways. So this is where the information technology comes into play.
This so-called 6R thing that we have.
Right.
Yeah, in a different context in the Navy.
But sounds very, very similar, right? Yeah. But so the bottom line here is smart manufacturing is really about looking across the enterprise, but you don't get anywhere other than just incremental change unless you actually change the manufacturing structure. So it's really about breaking down these compartments and thinking about it from an enterprise standpoint. The other one is a definition we've used quite a bit, and you can kind of read it from a data standpoint. Where the opportunity rests, we've looked at probably 100 different applications with different companies, different industry sectors, and so forth. And they all kind of boil down to these three areas. And I wanted to just kind of get these on the table and get the vocabulary on the table. The first is very simply just untapped market productivity with performance. So if you can do things with the enterprise much more dynamically, there is a huge amount of opportunity. What we have tended to see is if you think about it from a revenue standpoint or a savings standpoint, almost everything we look at starts at about 15% and then goes up from there. So if you think about 15%, that's actually quite a substantial savings. And so you can think about number one as 15%, and then when you begin to understand the process from its enterprise standpoint, it goes up from there. Real-time data and modeling to qualify materials. This is the part about if you can really understand the precision of the materials, really understand the precision of the parts that you're talking about, really understand where they're coming from, and if you can use data to drive this precision, there actually is significant revenue opportunities moving forward there, especially as we move into trade spaces that have more customization, value added to these different products that are based on individual customers. And then there's a whole set of operational practices that we've been trying to create a vocabulary for that just get at these things. So intensification means, can I use data to just run my process better, use energy better, use materials better, and so forth. Virtualization is interesting because we're all used to like banking, we do this virtually, right? Or we're all used to having software pushed to us or updates pushed to us. Why can't we do some things similar in manufacturing? Why can't we run the businesses more virtually and then use those to drive the physical operating equipment and so forth? So this is what we're getting at with virtualization. Modularization is the term of pieces of equipment or operations, whether they're in different companies or within different line operations, can you mix and match them in some different ways and in a more flexible manner to make the products? So this is the agility question that gets brought up. Qualification, we've talked about, can we do in situ measurement, in situ qualification of a part or a product? Because if you can, you have a chance of controlling it. If you can, you have a chance of qualifying it and collecting data for it, with respect to a supply chain or moving forward. A good example of this is the pharmaceutical industry. Right now, how do you know that a particular medication, meets the qualifications that is intended? It goes to an offline, quality assurance sort of test. What if you could actually understand the process and know that coming out of that process, that particular medicine is qualified? Same is true for a lot of different parts. And then, again, I want to emphasize that one of the key drivers that's in play here is the manufacturing is not the same as it used to be. Steady state is kind of out the window. We need to stop teaching steady state. Not entirely. That's a heretic statement. But we need to stop teaching steady state. It's really about dynamics and demand response, agility. How can you move among products, contracts, all sorts of things faster and more easily? And if you can do that, there actually is a great deal of market potential going forward. So this is what we mean by this, and we want to start talking about this as a term of practice. It's really not a technology. There's a lot that gets put up here around Internet of Things and the Industrial Internet Consortium. And these are being used a lot. And I wanted to just kind of stress with this slide that if you look at Internet of Things, it actually is extremely broad. So if you look at the two together, we're talking about consumer products, we're talking about manufacturing, we're talking about cities, we're talking about agriculture, we're talking about transportation. So when you put all those together and think about the devices, yes, there's a huge number of devices that are being connected to various networks. But from a manufacturing standpoint, the breadth of those is so large, it's actually hard to get at the specific things with respect to manufacturing and that are peculiar to manufacturing. And so one of the things we want to do from a Smart Manufacturing Institute standpoint is actually look at IoT in a vertical sense and focus just on manufacturing. So this list of things to the left has come through a lot of discussions with companies. What are the things that are peculiar to manufacturing that we really do need to take into account? I won't go through all of these, but it's actually quite interesting. One is I end up on a lot of panels about drones and driverless vehicles and manufacturing. So why do the three get put together? Well, they're all talking about cyberspaces. They're all talking about interconnected devices on networks, but they're very different, right? It's very different to think about a cyberspace in which physical objects are moving around in it versus manufacturing where you have static pieces of equipment, and what's moving around is the product. That's moving from operation to operation. So when you want to think about security or you want to think about opportunities or revenue opportunities, they're very, very different. We want to focus in on those things relative to manufacturing. The other big one here is legacy operations and always operating. So industry in the U.S. is actually relatively old. And so there's a lot of legacy equipment out there, and everything was designed, we as engineers design stuff pretty well, right? It needs to last 50 years, and it continues to do so. So if you look at control systems, instrumentation, equipment, it's 30 years, 40 years, and it's still running, and no one's going to change it until it's not running anymore or it's not making money. So how do you think about smart manufacturing from a retrofit standpoint? And then the always operating piece is also quite interesting. If you talk about changing out a piece of software, it's quite one thing if that piece of equipment stops. You can go out, stop it, test it, and then put it back on. But how do you do testing and evaluation during an operation? That becomes very, very interesting as well. The other things I think are, you can read those, but wanted to kind of get this flavor on this. One other thing with the triangle that we use as kind of a rudimentary reference architecture, I'll go into one in more detail. IoT and IIC are all about the infrastructure and the device connectivity. Smart manufacturing is interested about what happens beyond that. So yes, we're very, very interested in IoT, and we watch the standards and where they're going, but we're really focused on what do you do after you have these devices connected? What do you do when you have the analytics? How do you actually deal with the data? And if you start moving up this pyramid, the pinnacle is what are the advantages of actually sharing some data or sharing some capabilities, sharing some patterns of activity, and where does reusability exist? So I'll talk about that a bit more in a minute as well. So I hope that gives you a little bit of a flavor for at least some definitions. And what I'd like to do is dive into some examples and tell you a little bit about what Sesame is. First of all, Sesame as an institute is a collection of 5 regional manufacturing centers, as we call it. So you in Connecticut are actually associated with a regional manufacturing center, which we call the Northeast. And we base the operation at RPI, the Center for Advanced Technology Systems, and but it includes Connecticut, major effort, major kinds of capabilities being brought to the table, as well as MIT with Penn State, and then the industry in the area is what is of great interest here. And so you can think about the kinds of industries that are here. You start seeing capabilities building out. So with UTRC and aerospace, glass is large here, microelectronics and so forth. So these are the kinds of industries in your area that there's been a lot of expertise built up. And so what we're interested in doing is now embedding smart manufacturing in this region relative to those kinds of industries. And if you go around the country, you'll see other, call it, areas of emphasis relative to the manufacturing companies. And this is a way for us to let these things develop with the differences around the with those differences around the country. So it's a powerful concept in our opinion. Anyway, it's the idea of how do you take the institute to manufacturing as opposed to trying to get the manufacturing to come to the institute. We want to take it back out this way. So that's the objective. The other thing about this is we are Department of Energy funded. And so I'll let you just read through the goals on the right-hand side. So there's an energy focus. But the main thing I wanted to bring out with this slide is we're not an institute about going after energy. Yes, we have an overall objective of reducing the consumption of energy or intensifying better use of energy. But the way to do this is actually to improve performance, improve precision, and so forth. If you do those things, then energy savings or reduced energy consumption is an outcome. So one of the things we will say over and over again is if you go after energy in its own right without dealing with productivity, workforce, all these sorts of things, you don't get there. But if you go after productivity, revenue, better use of materials and so forth, energy falls out and actually becomes a competitive advantage. So we're actually looking at not to reduce costs, but actually build manufacturing up in a way that there is growth and opportunity for reinvestment. And then that's how one can get at a reduced energy consumption.
Typically, what is the energy cost in manufacturing? What fraction?
Well, let's see. If you look at it across the U.S. and across all energy, it's about a third. So third residential, third transportation, third energy, roughly speaking.
No, like a manufacturing, like what is the cost within a manufacturing facility typically? I guess it depends upon
but yeah, you mean in a facility?
Right, like
it's a little hard to do.
Labor.
Yeah, it's hard to. It's actually hard to say because it depends on the segment, the industry sector. But if I go back here, the DOE actually defined what they call energy-intensive industries. So these are oil and gas, chemical, cement, glass, and so forth. That actually represents probably about 75% of the manufacturing energy. If you get into aerospace and some of those which don't use energy, but the parts do, now you add up the rest of it. So even our institute is probably at about 20% of the total manufacturing energy use. Yeah, the other thing to point out too is well over 90% of manufacturing is in small companies, small and medium companies. And so we're really talking about lots and lots of small companies, and then we have to work with a large company. So that's where the supply chain comes into play. It's an important question. So let me take you through a couple of really quick examples to kind of illustrate what smart manufacturing is about, and then I'll get into some of the technologies. I particularly like this one. This is a supply chain example with General Mills, and the plant site here is in Minneapolis, Minnesota. But what I'd like to say is that we have a little girl over here eating Cheerios. And what I'd like to ask you to think about is, we've all eaten Cheerios. Take a single Cheerio. And what I'd like to convince you is that Cheerio is an advanced assembly, and it's made out of an advanced composite material. So think about it. But what I'll show you in a minute, the gluten-free actually brings out the advanced composite material aspects of this. If you think about a Cheerio, it actually comes with the oats from the farm, but it better be pesticide-free, it had better be metals-free, it had better be gluten-free in the case of General Mills, and if it's not, you've got a contaminated material, so you actually have to qualify that material to a very high degree. And if you just to reemphasize the seriousness of this, you may be aware that General Mills went through a recall that cost them a huge amount of money just about 6 months ago, because what they had happened is they had mixed non-gluten-free oats with their gluten-free oats. Someone got sick, and it created a whole recall, and that's a very, very serious situation. If you think about aerospace, it's not a whole lot different than, did this part come from China? Can I qualify this, to go put this in this assembly? It's very, very similar. If you think about a Cheerio as an advanced assembly, and I'll show you in a minute, where'd it go? Oh, I took it out. Oats from one farm is not the same as oats from another farm and oats from a third farm. And so when we bite into a Cheerio, it tastes the same coming out. So how does that happen? How do we hit that geometrical shape? How do you get that taste to be the same, even though there's a huge variability on the raw materials coming in? There's a huge amount of recipe management and so forth, to make this product coming forward. So there's a whole supply chain aspect that's in place here. What actually happens in General Mills, and I'll kind of work from right to left. Customer in this case is your grocery store, could be Walmart. And General Mills actually has to forecast our demand for Cheerios. Their forecasting algorithms are about 35% accurate. So you can imagine what happens there, right? That's not very good. It's just not good. And so they forecast with only about 35% accuracy. So boxes of Cheerios.
Over what time? Any
What's it?
particular horizon or just?
It's relative to how many they can make and the volume of their plants around the country versus how much we're going to eat, right? And the forecasting of that is actually not good. But when the forecasting is off, what happens is that box of Cheerios sits in the distribution center. If it sits in the distribution center, longer and longer time it's there, the greater the chance of it being contaminated. And so the better you are at a demand response with respect to Cheerios, the better you are with the safety of that product, and obviously the better you are with the revenue side of it. So what General Mills has been on a track to do is, how can I get closer and closer to demand response? Box off the shelf in Walmart, box on. How close can I get? And to do this, it actually has required huge investment in the factory side of this, connecting all the different operations, all the preparation operations, et cetera, in the middle. But what they haven't been able to do is solve the supply chain side of this. Oh, I had the pictures out of order. This is the answer to an oat is not an oat is not an oat. They come in from all different kinds. But you have to make the Cheerios taste the same. So the supply chain side of this, though, is actually quite interesting. This is just actually a sort of a graphic of the bin management system, or the silos that exist at the Minneapolis plant. And you can see that those silos have all different kinds of characteristics of those oats sitting in those silos. So if I'm going to make a certain amount of Cheerios, I need to know which silo I can use for that. I need to know to avoid these other kinds of silos. So how do I know what I have in these silos at any given time with the variability of the raw materials coming in? That's actually been the problem that General Mills is wanting to solve, and have been building some models out. So it's really a chain of custody model that's tied in with a recipe management kind of system. So smart manufacturing has been, how can I get all the way from the farm to Walmart end to end with the dynamics of the operation, the manufacturing, the supply chain in this particular case. A different example, this is Praxair, Port Arthur, Texas. And what you're looking at on the left is a little graphic of a steam methane reformer furnace. Just to give you the scale of this thing, though, it's about 5 stories tall. It's got 360 12-inch diameter tubes. You run methane in here. You break it down, and then the furnace heats it. Well, just what I'm trying to paint is a picture of a very large furnace, for this particular reaction that's taking place. And then those little things at the top, those are 96 burners that you actually use to control the heat distribution or energy distribution in the furnace. This thing's been around for 30 years. There's 900 of these things around the world, and basically no one's been able to see inside the furnace because of the harsh conditions in order to manage this. So what happens is you actually operate the furnace in a very conservative manner because you don't know what the energy distribution is inside, and you avoid then the burning out the tubes and mechanical failures and so forth. So the question was, what if we could see inside the furnace in real time? And so what was done was to put 8 infrared cameras around the outside of this furnace so that you could see the entire geometry. You could also see around all the tubes, and you knew exactly what the energy distribution was. You could then adjust the burners, even it out, raise the temperature, and this was worth reduced waste heat about 15% with a simple model, and another 15% with a more complex model. But what you're looking at here is the simple model. We reduced it by 15%. We went to a high-performance compute model, a computational fluid dynamics model, projecting another 15%. Reducing the cameras, it spun off another project where Praxair is now looking to reduce the cameras, offset that with modeling, so now you get a lower cost capital investment. But in other words, though, in smart manufacturing sense, this is about new sensors and new models, image, real-time control, MPC control, moving these things forward, and it's had significant impact on a legacy operation. And then where it gets very, very interesting is Praxair has 20 of these around the country. And so if you think about, they already manage their operations from a business standpoint, but what if you could see the operations from an operating standpoint? So we go to Port Arthur, Texas, you go to the second location. The demand is changing around the country, so you basically can start adjusting the operations. And so now you get this sense of virtual enterprise, on a national scale that's then managing the physical facilities around the country, and you tie them in with the distribution change. This is a huge energy savings for Praxair, but what the essence of this one was not an energy savings, it was actually energy productivity. They were able to make so much more product, they were making so much more money, that's where the gain actually came. So it wasn't a reduction in energy consumption, it was a significant increase in productivity. And then one more real quick one here, just to kind of emphasize one other kind. This is in Scranton, Pennsylvania. This is a General Dynamics metals fabricator. What they do is they make anything that's got kind of a concentric shape. So artillery shells, pipe fittings, a variety of things made out of steel. But the way it works is you bring in a steel billet on the left, you go into a forging press. This is a massive piece of equipment, heats it up, and then just presses a concentric hole inside that billet so that you get the general shape, but it's got to meet certain tolerances. You go to you shape it, you go to a heat treatment furnace in the middle to basically set the metallurgical properties, and then you go to the machining side, to actually shape the part to whatever the contract is requesting. This is an example of a legacy operation that's been around for a long time, where each of the operations was compartmentalized. So literally, you just got the part from the forging press, and then someone handed it over, and it kind of waited there for the heat treatment and so forth. And so the smart manufacturing aspect of this was, what if I looked at the whole operation at one time? And what I could start doing when I did that is, what if I started managing the properties in real time? So the properties on the first part are geometrical, the properties in the second part are metallurgical, and then the properties on the right-hand side are finished product. What if I looked at those all together? And what that allowed me to do are things like, if that forging press started going out of tolerance, I could shut that thing down, put it in maintenance, and if I planned that, I could manage the energy on the downstream processes, as well as save a lot of energy and machine wear on the machining side by just making sure I did the maintenance at the right time. On the heat treatment, I could optimize that in the normal way, but what I could do by having the properties, the geometrical and the metallurgical properties managed, I reduced the number of defective parts tremendously. And these are all done with a off-site test. So by doing this more in situ, I can save a lot. And then by putting these two together, this upstream stuff together, I can save a huge amount on the machining costs, which we're using a lot of electricity, a lot of machines, and so forth. So looking across the whole thing, this actually was a 20% savings on the plant, just looking at the entire line operation. So no big news there other than how do you get these things pulled together?
So how did you guys come up with this? So you must have gone through a lot of interviews and try to understand where the issues are, right?
Yeah, you have to sit down and you actually have to have a concept,
Right.
That basically becomes a business plan or a business model, and then drive it from there. But what I'm also trying to describe too is, invariably we would start off with a concept that would make sense, have a real business value, would meet ROI sorts of constraints, and then invariably we'd find new places to go after you've done the first part of the project. So that's where the savings actually accrues.
Yeah. If I did predictive maintenance on the first part, I would say so.
Right.
You must be informed by some data or from experience. No?
That's right. So this is all about modeling for predictive maintenance, which they hadn't been doing. They were trying to kind of guess at it before. Yeah.
Make a comment. Early 2000 at Ford, I spent a few years there, and they built this engine block manufacturing line, which was completely automated. They would do the casting, they would create the casting, do the heat treatments, everything up to machining. The whole thing was manned by 10 people. It was completely automatic. It was doing similar processes for different product. So I just wanted to point that out.
Was this the 150 when they moved to the aluminum?
No, it wasn't. Not for 150. I'm not sure. I don't remember exactly what engine they were doing this for. The company that built it was a Swiss company, I think. But it was just marvelous.
Yeah. Ford was a leader in this exact same kind of thing. So I'm not sure we're talking about the exact same problem, but they had Ford was, I think, really big in doing this. So, but let me take a break here. So this is what we mean by smart manufacturing. It's being able to do this. Now, I'm sure you're all thinking, well, we've been thinking about this and we've been wanting to do this forever. So this is the point. What we're interested in smart manufacturing now is how can I do this easier and faster? So the real issue is how do I enable this kind of thing so that I can do it, at least we like to talk about being able to do this at about a tenth the cost of what it's done right now and do it at a greatly accelerated rate. Right now if you put a software system into a company, the multiplier factor of that installation is a huge number. It's a huge cost, and it tends to be a one-off system. And so the question is, how can we enable us to do it more accelerated in a faster way? So, I stuck this one in. So where we started going down actually has a lot of parallels with healthcare. So I thought I've stuck this in because maybe it relates to this. But if you think about what's been happening with healthcare, right now it's become less and less going to a single place. You go to an urgent care for this, or you may get more information from a pharmacy. There's more and more sensors, wearable sensors that are feeding data in, and so forth. If you can get that stuff integrated in a right way, and you start working this from a patient, basically a patient record standpoint, if you can have that in an integrated fashion, your healthcare goes up. So we're actually trying to do the same thing, and quite honestly, the product in a manufacturing plant is not too different from us being the product in a healthcare system. So if you think about that, so what we're really doing now is saying if I can overlay these different systems, modeling systems, data, input, interfaces, and so forth with an overall system, we should be able to enable this better. And so what we call this platform, we call it the Smart Manufacturing Platform. So what I'd like to do is kind of take you through some of the things that we've been building out from that perspective and why. So I'm going to skip through the build on this. So one of the things that, and I was speaking to a couple of folks about this morning. So when you look at the manufacturing space, there's a lot of discussion about automation and control, and that's very, very important on the factory side. There are the business systems. For the large companies, it tends to be SAP system. For the small companies, it tends to be Quicken or something like that. We all talk about design, data and design, so training, analysis, and the integration, and the engineering. So a lot of that is taught in basically every university and all the training. But there's a space that's in between where you take the control system, the control level, we call it the micro level. What if I can extend that? What if I could put a integrated computational fluid dynamics model? What if I can improve the precision or something that's going on with that control system? The meso level gets at the manufacturing operational level. I'm making decisions about these different things, or I'm making decisions about contracts and so forth, and I need to change out conditions. How can I do that in a better way? And then the top level is basically the supply chain level. So if I'm working across companies in different ways. A good example of this one is Corning glass out here. So Corning actually makes glass. I guess that's a good reason to call it Corning glass. They make glass, but they actually need a material, and they actually contract the manufacturer of the material for specialty glass from another company. So right now, company supply chain, so it's a supply chain, then they go make the glass. How could you bring those two together, even though they're two different companies, so that they operate in an integrated, controlled fashion? So this is the space that we're actually talking about with this. And if you think about the Praxair example, it's the micro example. That General Dynamics is the meso space. And then the General Mills example is the supply chain macro example. So how do you get the data and everything put together in an appropriate way? So we started looking at the characteristics of this. We just simply call it end-to-end system. But if you look at every single system we put in, it has all these components. So no new news here. You can see this. But variable sensors to some kind of actuation. But what's significant are these purple arrows underneath. Multiple hardware sources, multiple analysis tools, multiple vendors, multiple platforms, and so forth. This is these one-off systems that we've been talking about. And so when we talk about advanced sensing controls platforms and modeling, the acronym up here, we're actually talking about how do you work across a heterogeneous environment that's going to look like this. So if I go back to General Mills and inside that factory in Minneapolis, this is all the different systems that are in that manufacturing execution space. And if you really want to get at demand-driven supply chain, like we were just describing, you actually have to connect the data of all these different systems into a coherent system. And so if you think about it, I'm connecting this data here, so drawing lines between all these different systems, you end up with a really complicated mix of stuff if you just start connecting the individual systems. So what we've been asking ourselves is, how do I unpack this, and how can I put some infrastructure in that's going to allow me to manage the integration of all these different systems as appropriate for some business objectives. So a way to look at this, as we look at it, is if you look at a typical system, like in this MES space, you'll see the color coding will become apparent in a minute. But one of these one-off systems tends to have different providers, different analytics. It could be on-premise, could be off-premise, but it's all kind of mushed together. And then if you want to connect it, you got to connect it to another set of things that are mixed together as well. And now you get a more complicated mix of things. So the thing that we're trying to ask is, how do we unpack this? But the point is that if we keep building these systems up and then try to interconnect them this way, it's just not an efficient way, it's a costly way, and we're just simply not going to get there. And I will point out that it's not secure. It's just not a secure way to do it. So we've been spending quite a bit of time with how do you span a heterogeneous environment. And so to us, a heterogeneous environment is multiple data sources, but it also is on-premise, off-premise, on-premise. How do you maintain the state across this? And you see the words enterprise workflow here, but one of the things that we've been doing is spending a lot of time from a technical standpoint looking at workflow as a fundamental construct. And I'm trying to find a good way to kind of stress this one, but because if you're going to put these systems together, you have to ask yourself, what do I put them together with? You can think of different constructs, but the one that kept making sense to us, or at least was used most often, that we could use was workflow. And so what we're really trying to do with workflow is basically take stuff that tends to be tightly integrated and ask ourselves, can we unpack it and can we reuse it? So you can see that I've taken data apart in 3 different broad areas, and with the recognition that there's a lot more to this, but you have to select data, you have to have a data model, you have to be able to configure the data for different things, you have to configure it again, you get different vendors involved. But if you can unpack these things, there are, at least as we've been building these out, you can reuse components of this and use this to spin up different projects more easily. And then, of course, there's the matter of on-premise and off-premise. So workflow is everywhere. PLCs on the factory floor, all kinds of companies put in workflow, but they tend to be compartmentalized to a particular product. The question we're raising is, how can you put a workflow together that's going to span multiple data sources and multiple vendor products? So this is what we've been building the capability out, and it's worked pretty well for us. If we do this, we can start using these data assets, this data model, and then we can start spinning up projects. So the General Mills example, data configuration for the oats problem, we're using a lot of the same data for a dairy problem, and so forth. We start spinning these up, and we start using many of the similar models. So now I can mix and match these models in a better way. And in their particular case, being able to go off-premise because there's so many of the suppliers is a very useful thing to do. So with that kind of idea in mind, now let me take us a little more, the technical structure of this. So reference architecture. Every system we're seeing now in a more technical way actually has these components. So you can see physical systems, network, data, abstraction, analytics, and so forth. So every system you're looking at is going to have these. But every system also has to have these vertical planes that you're showing here around data services, the human system interface, cybersecurity, interoperability standards. So the question we ask ourselves is, could we provide the vertical planes in a systematic structure so that those don't need to be reinvented, and you can slot in the horizontal planes more easily. And now you've got something that is basically an integration service, if you will. So we were talking about open this morning, so this is where we get to this. So from our standpoint, what we're really trying to do is make the vertical planes open and then put commercial products or open source or whatever product is selected in the horizontal planes. And we do this by basically, I'm back on our pyramid chart, but you can see open architecture, so we want to be vendor agnostic, so that's the usual APIs. Open access is a business side of this, which is making it low cost for small, medium, and large companies. The open marketplace, talk about composability in just a second. But you need to have software of these libraries and the ability of the data services, and then the marketplace for the ability to put innovative products in there in different levels of products so that you get into the development phases going forward. And one of the most important things is the trusted data broker. So this is the notion that any proprietary system, most companies don't want to share their data with a proprietary system. Alison, Tim, you can comment on this one. But if there could be a trusted data source in the sense of a third party that is credible, now there's at least a more open discussion to have on that. So that's where we're trying to go with that piece. So you'll notice the one thing that's missing from this reference architecture is this workflow as a service. So what we've actually done is built this whole system up. And so you can see the the horizontal planes now. What we do is go to a commercial provider, And we don't need to reinvent data connectors. We don't need to reinvent Historian or private virtual computation. There's cloud providers out there. So we've been slotting in commercial providers for all of these horizontal pieces. The one that does not exist out there is the workflow as a service. So this is actually where we've been building out one service that doesn't exist and making that basically an institute service. Then obviously down below you see these machine and human interfaces. We put all those kinds of capabilities in. Now the other thing that's I think a very interesting concept, but I'm biased, but you can push back. The right-hand side is actually trying to ask the question, when we build one of these systems, how do we do it? And most of the time what we do is, if I have an existing piece of software, most of the time what I do is I'd like to go to a pre-existing design that's been used for something that's kind of similar, and then I'd like to adjust it. Rarely does a system get built from scratch. Now, I know we do it in the universities all the time, but the question is, can we reuse these systems that have been used out and about already? So on the right-hand side, what we're talking about is a configuration. So an example here is the steam methane reformer. If I've worked through on that kind of furnace how to configure the data, I know that hourly averages work. I know how to get rid of the outliers for that kind of furnace. I know how to think about the time constant of that data. If I've done that already, why can't I use that configuration again for a similar geometry of furnace? So that's actually what we mean by a data configuration. Then obviously if you have a piece of software and you've built up a certain kind of model, why can't I reuse the configuration of that model? So one of the things we've been doing is the notion of reusable configurations, and then the marketplace is not software as a service, it actually becomes configuration as a service. But let me give you an example. This is ANSYS Fluent. We built a high-performance compute model for that steam methane reformer. And I'm assuming some folks in here have done some of these kinds of models. They're really quite extensive to do, right? So what this one required was to basically work the kinetics for a single tube, get that right, get that matched, validate with some data. And it took literally 6 months to get that one figured out. A lot of development time. Then what happened is once the kinetics were worked out, built out a miniature model of 4 tubes, 3 burners, and then started working with mesh and initial conditions, to be able to converge an ANSYS Fluent model. That took another 6 months. And then once that was done, then we had to basically expand to all 360 tubes. Now you've got to really worry about the mesh size. Now you've got to really worry about the initial conditions to converge this. That took another 6 months. So we had a year and a half's worth of work just to develop that one model for that furnace. So the question here is, why can't I use that mesh size, or that mesh discussion? Why can't I use the, some reference initial conditions? Because I know those are going to converge within at least, some confidence levels of that geometry. So one of the things we did was look at the sensitivity, the parameter sensitivity around those geometries. We're able to define where this would work and then start putting those in as a configuration so that you don't have to reinvent all the computational side of this HPC model. But that's just one example because you can think like this on just about any of these. So if I put all this together, this actually takes us to cloud. So we did not start off with cloud as a solution. We got to cloud as a solution. And so if you start thinking about, I really want to do these apps and these composability, this end-to-end workflow and so forth, cloud actually brings us a lot of interesting capability that you just can't get by putting infrastructure on a given plant premise. And obviously, if you're going to do interesting data things and it makes sense to transfer that data to the cloud, you can do some very interesting computational things that you couldn't do beforehand. But anything that's supply chain almost invariably will take advantage of the cloud. So we started looking at all of these kinds of broker and integration services from a cloud standpoint. And it actually becomes quite interesting because now we can get into the virtualization kinds of ideas in a much, much better way. And this whole notion of being able to take data to applications as opposed to only taking applications to data opened up a very large space for computation. So what we've done is built this out. And we've got this running we call it a production prototype. But from an institute standpoint, this thing is up and running. We're now expanding it and scaling it forward. But essentially what the SM platform is, and we use the term wireframe, it's a set of services that allows us to slide in this marketplace. It already provides the cloud management, orchestration, the security, those vertical bars that I was showing you. Those all exist, and what we do then is slide in, as I said, the commercial application pieces, and then we can start doing this composability. So we've been building this out for a while. This is what it looks like.
So the marketplace is where you'll have all these vendors providing.
Yeah. Actually, we have a deployment layer which can stay more steady, but people do slot things in and out. But the marketplace is much more selectable. It's more the direct application space.
Are there fees for that, or?
Yeah. Well, let's see. Some of this is to be determined, but the idea is the wireframe does not cost anything. It's part of the institute. And then the applications in there will depend on what they are. Those will be fee for service in the production sense, but as they're developed, they're just part of the projects going forward. But if you think about this, and I put a very quick list over here, but these are really quite powerful concepts. One is the notion of certified app configurations. So that's different than certified software. It's if this application has been used for a steam methane reformer, I can know that it was used for this kind of steam methane reformer and then have that validated. There is a very important notion here that you have to kind of think about a bit. If you go back to the internet, right, one of the things that was most powerful was not a lot of complexity, right? It was actually just a huge amount of stuff that's actually pretty simple, but you had a search engine that you could find it. And so one of the things that's really quite interesting to us in this configuration space is with the cloud, we now have the capacity to build that configuration space into a huge, just like an app store, right? It could be a huge amount of variations and different pieces, just slight variations. But if you could have a search engine to find them, you actually get to something that's internet-like from a manufacturing standpoint. And if you can compose and reuse those, now you've got something that is quite powerful. That's where we bring in that workflow construct, because we will put these configurations into a workflow-ready state. Now you can bring them together more easily. I did want to emphasize DevOps for manufacturing. So one of the most powerful concepts, I would argue, is the ability to try something out, see how it works in an operational setting, learn something, and then change it, as opposed to doing a massive design and have it try to stick for multiple years. And what we are down the path now with these sorts of things is that development approach that starts looking like we do in the IT space. And again, I'm putting concepts out here because we have to develop these from an institute standpoint. But what we have been able to do with the projects to date is that we go in this marketplace, we create these test beds by just simply building up an account. We can spin up different accounts for different kinds of modeling, different modeling efforts, different projects, and so forth. So this is actually what the steam methane reformer project looked like. We had 4 or 5 projects going at the same time with different people being involved, using the data in different ways, and they had different accounts. I'm running out of time, so I'll skip through a couple of things. Another thing an idea I wanted to leave you with is security is really important in these systems, but actually security is a friend, not just an enemy here. So one of the things we can do is as we build out these configurations, what you can do in the cloud is just use security to manage those. So what we're doing is just using public key, private key, so it's a fairly simple kind of security mechanism, but if the data for the metrics modeling needs to be constricted in some way for that particular team and a different way for another project, you actually can now, in a very granular way, use security to say this group can use this group cannot use this data. And so you get this granular management of the data. And then the granular management data actually helps the security of the system anyway. So in this particular case, we did a project with Emerson Controls. Praxair did not want Emerson to see some of the data, so we managed that data very differently than we did with the modelers doing the steam methane reformer in the top. And we just used public key, private key, and it worked very well. On the composability, very quickly here, we were able to start doing these things. If you think about the engineering of these, we actually used we built a workflow first. So you build a data model of that workflow, build it first. Now you've got a structure with which to do the development. And so this workflow was built out first, and then as the project progressed, we started trying different methods, different analytical techniques, different data configurations. We started switching the ANSYS Fluent model in and out for statistical models and so forth. But the workflow allowed us to move back and forth between these different configurations in a straightforward manner. And I did want to leave you with the thought that security is an elephant in the room. So this is a complicated slide, but it basically is more what you tend to work with, or we see in the plant situation. So a plant tends to have all these different zones, and so you're connecting cyberspaces within a plant. If you're going to cloud, now you've got another cyberspace. You've got to connect across the internet. You've got all these firewalls to deal with. They're going to affect performance. And then the red boxes actually represent a whole set of new issues that we're trying to deal with. So copies of data. One of the things that you don't want to do is keep copying data everywhere, but maybe you can read it. And so you have different opportunities to deal with that. Regulation. No one's asked the question about liability, whether you push and pull data. There's the training pieces of this and so forth. But I just want to leave you with a thought on the security. And I'm just about at the very end here. If you look at the economics of having this kind of enabling capability, it actually becomes significant. So across the several projects that we've done so far, you can start seeing the acceleration. The acceleration is tremendous because you don't need to reinvent everything from the software as a service level. And then as we build out these first of a kind, this DevOps kind of approach actually starts accumulating capability. That's what the top row is basically suggesting. So I will end with why is UCLA interested in this kind of project? So University of Connecticut can think about this as well. So the research funding reallocated to institutes, that's obvious one. The public-private partnership. But we've been asking ourselves, what's the value of data and algorithms that are developed on the campus? And can we put those into operation better? So we're looking at it as, heavily as a tech transfer mechanism, and obviously a way to get access to the problems. We were talking about that this morning. The researcher capabilities and discovery, and cross-linking that across the entire country. So the ability to work with researchers. And then the platform actually gives a way for the researchers or the industry to come together and work together on these. I haven't stressed it too much, but workforce training, education is actually the key to all of this. So how do we start building up the analytics, data capability in the operations space, and not just the information technology? And then there's a public mission piece of this, as I'm showing. But UCLA was interested in all of these, from a state as well as a national standpoint. So when I sold this to the chancellor, this is the list of things I talked through with Gene Block. But anyway, let me end there. Our slide. This is what smart manufacturing is. It's about stepping back, thinking in a macro view across the enterprise. It's not about any one narrow thing. How do you intersect these things? And the left-hand side is actually a list that NIST put together, basically saying this is if you can get these things intersected, you actually have a huge performance, revenue, economic opportunity from a manufacturing standpoint. So a very fast cut. It's a breadth cut, but I hope it gives you a flavor for some of the things we're thinking about with the kinds of problem and then the infrastructure, to enable these in a different way. So if you came away with a little bit of that, I was successful. So thank you very much.
Any questions?
So a lot of the things that you talked about, you will be imposing a data layer, data management layer that's composable. Mechanical systems are not composable, really, which is why we're still working on design and manufacturing. How do you see interaction between this composable layer of data and the non-composability of the mechanical systems. In other words, would you be able to apply this structure to a mechanical manufacturing environment?
Yeah, so that's actually a pretty interesting subject for discussion, right? If I'll take it where I take that kind of discussion. So there's a lot of discussion out there with digital twin and then the physical system, and so the question that's being asked is, can I compose the physical layers into an overall process, right? And then you start layering digital twin in there, and can I use those in some way? One of the things we'd like to say is that what we're really focusing on is not the mechanical system, but on the data flow across those mechanical systems. So we often get asked, aren't you just building a model of that system? The answer is no. We're actually building a data flow model for an objective. And so as long as we're in that space, that's where the composability lies. Because I agree with you, you can't compose the mechanical systems. So the workflow is actually around key performance objectives and then what the data flow needs to look like. But it's a really important topic because it gets confused, I think, with what we're doing.
Any other questions?
Yeah. How do you get companies to kind of buy into your system?
How do we? Let's see. There's two things going on, but I can turn to UTRC. But what we see across the companies is, number one is the need for doing something differently in an enterprise standpoint. This demand response, agility, working with data is being very well recognized. So the companies are very interested on, I know I'm going to need to move in this direction, so how do I do that? So that's one part of it. And then the other part of it is the notion of some infrastructure and then being able to work through some of these kinds of problems as a group. And so that's actually the role of the Institute. The issue is intellectual property. And so you really just need to sort through that one because the Institute's actually not trying to collect individual intellectual property, but it is trying to manage combined or composite intellectual property, on behalf of the Institute. So there's some strong forces against it, but there's some strong forces now that, Alice and Tim, they're just, everyone's seeing the need to move in this direction, and the Institute is providing some opportunities and ways to get at some of the big problems that are out there. Security is an elephant in the room. Infrastructure is an elephant in the room. How to get out of a vendor space that is trying to compartmentalize more, from a revenue standpoint, is an elephant in the room. So the Institute is about trying to get at those kinds of issues.
I have one more question. How would you define success of this activity at the end of the time frame that you're looking at?
Yeah, well, let's see. That's right. There's two things that are stipulated in the DOE contract itself. One is that we need to basically show 15% energy consumption of energy, a reduction of energy consumption in our test beds. So as we move forward, and there will be a considerable number of those. We also are stipulated in showing a pathway to 50% energy productivity. So that's on a per unit basis. Within the application, we also did a fairly deep dive. We have been starting with that 15% because we've been seeing it across the board. So within 5 years, we would like to be showing the 15% reduction with 3 to 5% market penetration. Within 10 years, we would like to start seeing reinvestment with about 12 to 15% market penetration. And then we're also looking to show about a 3 to 4% increase in the technology, call it the smart manufacturing technology supply chain. Those that provide this kind of technology, they've been kind of flat right now, and so we think there's a lot of room for growth as these things start becoming adopted. So those are there's a DOE and then self-imposed moving forward.
I think the other big success item is making the Institute sustainable. So
the Institute's got to stay going. Yeah.
It has to stay going after the DOE funds are used up.
It's about $70 million, right, from DOE?
70. Yeah.
70.
Yeah, how does this work? For example, UTRC and you kind of partners, suppose they submit some proposal or something. How does this activity get funded and executed?
Well, let's see. The short version is that we do have a technology and a business and technology roadmap. And so that's actually going to stimulate a call for proposals, which should be out here very shortly. And then we're expecting UTRC, probably with University of Connecticut and CCAT, to actually put in a proposal. So there's a partnership that's established, a budget that's established. It'll be a combination of cost share through the partners and then an expectation of the DOE funding. And then those get put together into an overall, we call it a testbed project.
Thanks. I think we have maybe about 5 minutes late. Thank you very much.